In this video, we're going to look at Gaussian elimination, and we're first going to do a quick warm-up example. The question is the matrix in REF, in other words, is the matrix in row echelon form? Well, to answer this question, we're going to circle the leading non-zero entry in each row. In the first row, the first non-zero entry is this one. In the second row, the first non-zero entry that we see is this one. And the bottom row consists entirely of zeros, so there's nothing to circle down there. Now, a matrix is in REF if two properties are true. First of all, the leading entries that we've circled must move down and to the right. Second of all, any zero rows must lie at the bottom of the matrix. So yes, both of these properties are satisfied, and yes, this matrix is in row echelon form. So now let's look at a typical example of Gaussian elimination. We'd like to solve this system here. The first thing we'll do is we'll set up what's called the augmented matrix for the system. So the way I like to set this up is just label the columns here. The columns are going to represent our different variables. The vertical bar represents the equal signs, and over on the right side we've got the constants. So we're going to be filling in the coefficients of our variables. That first equation is going to correspond to 2, 3, 4, and then we've got a 17 over here, and we'll fill in the next two rows similarly. So we've got 3, 6, 1, 1, and then 2, 3, negative 1, negative 8. Now the goal is to get this matrix here into row echelon form. Now before we start our calculation, let's do a recap of the elementary row operations that we're allowed to use to solve this system. So there are three types of allowable operations. First thing you can do is you can swap any two rows. So let's say swap row I and row J. Second thing you can do is you can multiply or divide any row through by a non-zero constant. So you could do something like row I times negative 3 or row I divided by 2, I'll just say etc. So those are examples of the second type of row operation that we can do. Third thing we can do is we can replace any row. So let's say replace row I with itself plus a multiple of any other row. So you can replace row I with row I plus k row j. So I'm going to put a box around that. Those were our three types of elementary row operations. So typically what I like to do in starting Gaussian elimination is to get a 1 in the upper left-hand corner. Technically this is optional when you're doing Gaussian elimination, but I find it makes the calculation go a little bit more easily. So probably the easiest thing to do here would be to take row 1 and divide it through by 2, and that will create a 1 in this upper left position. So taking this first row here, dividing through by 2, we'll have 1, 3 halves, 2, and 17 halves. The other two rows are going to stay the same, so we'll just recopy those. And I like to double check my work at each step. So yes, we've divided through by 2 correctly there, and yes, we've recopied those bottom two rows correctly there. So that looks great. Now our next goal is to get zeros in the rest of that first column. So we want to eliminate the 3 and the 2 here in that first column. To eliminate those, we're going to use the third type of elementary row operation. So to get rid of the 3, I'm going to go row 2 minus 3 times row 1. Okay, we always take the row that we're on minus an appropriate multiple of the row that has the 1 in it. That sort of operation will create a 0 for us. And in the bottom row, if we want to get rid of the 2, we'll go the row that we're on, row 3, minus an appropriate multiple of the row that has the 1 in it. So row 3 minus 2 row 1 will give us a 0 there. All right, so let's fill in the rest of this matrix. I'm going to recopy the top row, since that is not changing. And then we'll do row 2 minus 3 row 1. So that's going to give us 0. Now, anywhere where you need to do a little bit of a calculation, you can do some scribbling down below. We need to figure out what 6 minus 3 times 3 halves is. So that would be 6 minus 9 halves. Now that I've written this down, I can see that's going to be 12 halves minus 9 halves. So in other words, 3 halves. All right. And then we're going to go 1 minus 6 gives us negative 5. And again, here we might want to do a little bit of scribbling. We're going to need to do 1 minus 51 halves. Okay, so now that I've written that down, I can see that's going to be 2 halves minus 51 halves, so negative 49 halves. Okay, continuing with our bottom row. 2 minus 2 gives us 0. 3 minus 2 times 3 halves, that's like saying 3 minus 3, that's going to give us 0. Negative 1 minus 4 is going to give us negative 5. And then negative 8 minus 2 times 17 halves, that's the same as negative 8 minus 17, so that's negative 25. There we go. And I'm just going to scribble through this. This was just our rough work here to get those intermediate numbers there. All right, now at this point, our matrix is in REF. We don't have a 0 row, but if we did, it would be located at the bottom of the matrix. The main thing that we're looking for here is that the leading non-zero entry in each row, if we trace out the pattern of those entries, they're moving down in the diagonal here. So they are moving down and to the right. Yes, our matrix is in REF. So I've just recopied our matrix from the previous screen. Now that we've got our matrix in REF, what we're going to do is solve the system by back substitution. So this is one of the things that makes Gaussian elimination different than the full Gauss-Jordan elimination. In Gaussian elimination, you only take your matrix as far as REF, and the trade-off is now that we have to do a little bit of additional work. We have to do this back substitution to be able to solve the system. So it may help to label our columns. Remember, the columns represent our variables x, y, z, and then over on the right side we've got the constants. We're going to start at the bottom of the matrix here, and this bottom row is giving us the equation minus 5z is equal to negative 25. So dividing through by negative 5, we've got z is equal to positive 5, and we found the value of one of our variables at this point. Now we're going to slowly work our way up the matrix here. Looking at the second row, that says that 3 halves y minus 5z is equal to minus 49 halves. And we're going to take our known value, z equal 5, and plug that into this equation as well. So we'd have 3 halves y minus 25, because we're just plugging in the 5 here. So 3 halves y minus 25 is equal to minus 49 halves. All right, so we'll do a little bit of algebra here. 3 halves y is equal to negative 49 halves plus 25. We might want to multiply that 25 here by 2 over 2 just to get a common denominator. So in other words, 3 halves y is equal to 1 half. All right, now multiplying both sides by 2/3, that tells us y is equal to 1/2 times 2/3, or in other words, y is equal to 1/3. So I'm going to put a box around that. We've now found the values of 2 of our variables. Now, continuing to work our way up this matrix here, we're going to go up to the top row now. X plus 3/2 y plus 2z is equal to 17/2. And we're now going to plug in both of our known values. So plugging in z equal 5 as well as y equal 1/3. We've got x plus 3/2 times 1/3 plus 2 times 5 gives us 10. And that equals 17/2. So now just a little bit of algebra to figure out the value of x. X plus 1/2 plus, let's make this 10, 20/2. Okay, that way we can say x is equal to 17/2 minus 21/2. In other words, x equals minus 4/2, or x equals -2. So you could do this algebra here as quickly or as slowly as you like, it's up to you, but you should find the value x equals -2. So we have now solved the system. The values of x, y, and z are -2, 1/3, and 5.